Welcome to today's paper reading. Today's paper is titled, LGM, Large Multi-View Gaussian Model for High-Resolution 3D Content Creation. This paper was published on AR14 by Jiaxiang Tang and colleagues from Peking University and Nanyang Technological University. The abstract highlights the advancements in 3D content creation, noting improvements in both quality and speed. However, it points out that current feed-forward models, while fast, are limited in resolution due to intensive computation during training. To address this, the authors introduced the Large Multi-View Gaussian Model, LGM, a novel framework designed to generate high-resolution 3D models from text prompts or single-view images. The key insights of the paper include proposing multi-view Gaussian features for efficient 3D representation and an asymmetric U-net as a high-throughput backbone. Extensive experiments demonstrate the model's high fidelity and efficiency, maintaining fast generation speeds while boosting training resolution to 512, thus achieving high-resolution 3D content generation. Figure 1 illustrates our method's capability to generate high-resolution 3D Gaussians within just 5 seconds from either single-view images or text prompts. This rapid generation is achieved through the fusion of multi-view Gaussian features, which are efficiently predicted and rendered. The figure showcases the process of transforming input data into detailed 3D Gaussian models, highlighting the speed and resolution capabilities of our approach. Automatic 3D content creation is highly valuable in various fields including digital games, virtual reality, and films. Key techniques such as image to 3D and text to 3D significantly reduce the need for manual labor by professional 3D artists, allowing non-experts to create 3D assets. However, previous methods often face issues like slow generation speed, limited diversity, and low-resolution training. These challenges stem from inefficient 3D representations and heavily parameterized 3D backbones. In the realm of high-resolution 3D generation, current methods predominantly employ SDS-based optimization techniques, which necessitate both expressive 3D representations and high-resolution supervision. Techniques like Magic 3D convert NERF to DMTET for finer resolution refinement, leveraging hybrid representations to capture high-quality 3D information. Gaussian splatting is another promising method, though it requires careful initialization and densification. Efficient 3D generation, on the other hand, focuses on feed-forward methods that can generate 3D assets quickly after training. Models like LRM and Instant 3D have shown the potential for fast text-to-3D generation, though they often face limitations in resolution and fidelity. Recent advancements in Gaussian splatting for generation include Dream Gaussian and Jiaxiang, which aim to decrease generation time through various densification strategies. However, these methods still require significant time for high-fidelity results. Our work aims to address these challenges by investigating a feed-forward approach to directly generate a sufficient number of 3D Gaussians. The Large Multi-View Gaussian model employs Gaussian splatting to represent 3D data using a collection of 3D Gaussians. Each Gaussian is defined by a center, a scaling factor, a rotation quaternion, an opacity value, and a color feature. Rendering involves projecting these 3D Gaussians onto the image plane and performing alpha composition. Multi-view diffusion models generate multi-view images by fine-tuning on 3D datasets, incorporating camera poses to create consistent views. However, without an actual 3D model, inconsistencies may still occur. The 3D generation pipeline consists of 2 steps: generating multi-view images from text or image inputs using diffusion models, and predicting 3D Gaussians from these images using a U-net-based model. The generated Gaussians can be optionally converted to polygonal meshes. Figure 2 illustrates the pipeline of our model, which is designed to reconstruct 3D Gaussians from multi-view images. This process can be initiated with either text or image inputs, leveraging existing models, 44, 51, to synthesize the necessary multi-view images. Additionally, our model offers the capability to optionally extract polygonal meshes from the generated 3D Gaussians, enhancing the versatility and applicability of the reconstructed 3D data. Figure 3 illustrates the architecture of the LGM network, which employs an asymmetric U-net design featuring cross-view self-attentions. The network processes 4 images with camera array embeddings as input, producing 4 feature maps that are subsequently fused into 3D Gaussians. These Gaussians are rendered at novel views and compared against ground truth images for supervision. This architecture enables the generation of 3D Gaussians from multi-view images, enhancing the model's ability to handle complex 3D data. Figure 4 illustrates the efficient pipeline for converting 3D Gaussians into smooth and textured meshes. The process begins with training a NERF using the rendered images from 3D Gaussians on the fly. This NERF is then converted into polygonal meshes. Specifically, 2 hash grids are trained to reconstruct the geometry and appearance from Gaussian renderings. Marching cubes is applied to extract a coarse mesh, which is iteratively refined together with the appearance hash grid using differentiable rendering. Finally, the appearance field is baked onto the refined mesh to extract texture images. This entire process is designed to be efficient, taking only about 1 minute to complete. The experiments were conducted using a filtered subset of the Objaverse dataset, resulting in approximately 80,000 3D objects. The network architecture employed an asymmetric U-net with 6 down blocks, 1 middle block, and 5 up blocks, producing a Gaussian feature map of 128 by 128. Training was performed on 32 NVIDIA A100 GPUs over a period of 4 days, utilizing an effective batch size of 256. Figure 5 presents a comparison of generated 3D Gaussians for the image to 3D task. Our method is highlighted for producing Gaussian splatting with superior visual quality across various, challenging images. This improvement is crucial for effectively preserving the content from the input view, ensuring that the high-resolution 3D Gaussians can be transformed into smooth, textured meshes with minimal loss of quality. Figure 6 presents a comparison of our image to 3D method with the results from LRM 15. The comparison highlights how our multi-view approach effectively addresses the common issue of blurry back views and flat geometry in 3D models. This results in significantly enhanced detail, even in views that were not directly observed during the generation process. The figure visually demonstrates the superior quality and detail preservation of our method compared to LRM, showcasing the benefits of our multi-view diffusion models in generating high-quality 3D representations from 2D images. Figure 7 presents a comparison of generated 3D models for text to 3D tasks. Our method demonstrates superior text alignment and visual quality compared to recent methods. This enhancement is attributed to our multi-view setting, which effectively mitigates issues such as blurry back views and flat geometry, resulting in more detailed and realistic 3D objects. The figure illustrates the improved realism and text alignment achieved by our approach, highlighting its effectiveness in generating high-quality 3D models from text descriptions. Figure 8 demonstrates the diversity of our 3D generation method. We can generate a variety of 3D models even when provided with an ambiguous text description or a single-view image. This capability is attributed to the multi-view diffusion model, which allows for the creation of multiple feasible objects from the same input. The figure showcases the versatility and robustness of our approach in generating diverse and realistic 3D models. Figure 9 presents an ablation study on the designs of our method. The top left part illustrates that the single-view model can faithfully reconstruct the front view but struggles with the back view, resulting in blurriness. This is expected as the regressive U-net is more suitable for reconstruction tasks. The bottom left part shows that the model without data augmentation leads to more floaters and worse geometry during inference, whereas the model with data augmentation can better correct 3D inconsistencies and inaccurate camera poses. The right part demonstrates that training with fewer Gaussians and a smaller rendering resolution results in a model that can still converge and reconstruct 3D Gaussians, but with worse details compared to the high-resolution model. Our large-resolution model at 512 by 512 captures better details and generates Gaussians with higher resolution. Table 1 presents the results of a user study evaluating the quality of 3D Gaussian models generated for image to 3D tasks. The study uses a rating scale from 1 to 5, with higher scores indicating better quality. 3 methods were compared: Dream Gaussian, Triplane Gaussian, and our Large Multi-View Gaussian model, LGM. The LGM model achieved the highest scores in both image consistency and overall model quality, demonstrating its superiority in aligning with the original image content and producing more realistic 3D objects. In this work, the authors present a large multi-view Gaussian model designed for high-resolution 3D content generation. This model employs Gaussian splatting and U-Net, distinguishing it from previous methods that rely on NeRF and transformers. It addresses the challenges of high memory requirements and low-resolution training. Additionally, the authors explore data augmentation for improved robustness and introduce a mesh extraction algorithm for the generated 3D Gaussians. This approach achieves both high resolution and high efficiency in 3D object generation, demonstrating its versatility and applicability in various contexts. Thank you for watching.